Okay, now I want to do an example to show you how you can get all this information without plots, and then I'll also show you some plots, and hopefully we can make some animations and see what things look like just purely on the phase line versus what they look like as time series plots. So first let me go to your homework and pick out an example. Okay, here's a problem, homework 3, problem 2, and everyone has different numbers, but I'm just going to choose the numbers that were generated for me here. X prime equals this. So this is an autonomous differential equation because you see there's no t's on the right. So it's possible to do a phase diagram analysis. If there were t's on the right, then there's no way to do a phase diagram. At least there's no way to do one phase diagram because then your phase diagram would be morphing and shifting in time, which is quite a bit more complicated of a situation. Okay, so here I've written the differential equation down, and the task is to draw a phase diagram. So we want to draw a phase diagram. And this will help us answer questions like this question at the end. If x is a certain thing when t equals 0, so given the initial state of your system, then what will happen in the future? What value does x approach in the long term? So again, no solving required. You don't need to solve a differential equation to decide what's going to happen in the future. So it's quite powerful of an analysis tool. Okay, so first let's find the critical points. So this function here, this expression, is playing the role of f of x. And this is an autonomous differential equation. There's no explicit time dependence on the right side. Of course, there is implicit time dependence, because these are all x of t, right? And I'm just not writing of t. So f is a function of t because it's a function of x, and x is a function of t. But for the moment, I want to view f as though it's a function of the independent variable x. And then I'm going to take its derivative and get information using that derivative. So before I take the derivative, I need some critical points. So let's solve for the critical points. So I'm going to take the equation f of x equals 0 and solve it. So that's x, 4 minus x, 5 minus x squared equals 0. Okay, so there are, well, this is a degree 5 polynomial, so I expect at most 5 solutions. But in fact, I get 4 sorry, this is a degree 4 polynomial, so I expect at most 4 solutions. But in fact, I get 3 solutions. X equals 0, or x equals 4, or x equals 5. It just looks like x equals 5 appears twice as a solution. But no matter, let's just write down our critical points. There are 3 of them. X star equals 0. X star equals 4, and x star equals 5. So that's already telling me, no plots needed, how to start filling out my phase diagram. Here's x equals 0, here's x equals 4, and here's x equals 5. And these are all equilibrium solutions. So this is telling me about 3 very particular solutions to the differential equation. X of t equals 0 solves the differential equation. If you plug that in, the left-hand side will equal the right-hand side. Same goes for x of t equals 4, or x of t equals 5. Those are solutions. And they are the only constant solutions. All other solutions will be non-constant. So this finding critical points is the surefire technique for finding all the constant solutions. Okay, now we'd like to fill out the phase diagram with some arrows, like arrows that will help tell us, if x starts out somewhere between 0 and 4, then what will happen to it? Will it go towards 4? Will it maybe go towards 0? Things like that. So to find that information out, you can look at df dx. Or you can plot f. But I want to show you that you can do things without plotting if you want to. So df dx, now it's not a time derivative, it's just a derivative with respect to x. So treat x like it's the variable here. So here I'd have to do the product rule, right? Or, you know, I can multiply this out or something. I'm going to choose to do the product rule. So the derivative of 4 minus x is negative 1. And the derivative of 5 minus x squared is 2. Let me make some room here. Critical points were 0, 4, and 5. And the derivative of 5 minus x squared is negative 2 times 5 minus x. So I think we get that. And then plug in x equals 0, x equals 4, x equals 5, and see what you get. So at x equals 0, I get, so let me just compute this off screen. Sorry, no need to do that off screen, that was an easy one. So these two terms would die off, would just die because they're multiplied by x here, and I'm plugging in x equals 0, and this gives me 4 times 5 squared, which I don't care what that number is, I care that it's positive, which means that if I were to plot x prime versus x, then this is what I'd see passing through here. Or another way to think about it is, while x prime vanishes, so this is what I mean by x prime, while x prime vanishes at 0 at the critical point, I know that x prime increases with respect to increasing x. So if I increase x, then x prime will increase, because the derivative of x prime again versus x is positive. So if I were to go to the right here, then I would expect to see positive derivative, positive x prime. And if I were to go to the left, then I would expect x prime to decrease and become negative. So here I have an unstable equilibrium. Let's do the same kind of analysis, but at 4. So if I take this big expression up here, and then I plug in x equals 4 instead of plugging in x equals 0. Okay, now I'm getting bored of plugging things in, so I'm just going to go and do this in Mathematica and show you how you can do it to help save some time. Okay, so actually, you can even make Mathematica take the derivative for you. So let me go ahead and make the right-hand side here be... let me go ahead and define a function, f of x, to be this right-hand side of the differential equation. So treating x as an independent variable and sort of ignoring any implicit time dependence. Okay, so there I've got my f of x. And I could plot it if I want to. So this is one way to go. I would want to make a plot that includes 0 and that includes 5. So how about a plot from x equals negative 1 to x equals 6? Then, yeah, you can see the critical point at 0 here, critical point at 4, and a critical point at 5. I guess the critical points at 4 and 5 are kind of hard to see. Maybe if I do a plot from 3 to 6. Yeah, you see here. But I want to do this without the plot, so forget that. Let's try to do it without a plot. Just focus on the derivative. So to take a derivative of f with respect to x, you can do this in Mathematica. Capital D for derivative, and then the function whose derivative you want to take, and then the variable that you're taking derivative with respect to. Or actually, this notation works, f prime x. So there's the derivative, and that's the same one I computed here, I hope, if I did it right. Then if you want to evaluate the derivative at 0, I get 100, that's this number, which is positive, and that's all I care about. That suggests unstable equilibrium. On the other hand, when I evaluate the derivative at 4, I get negative 4. which is negative. So here I expect to see a stable equilibrium. So something like this, right? So so this is -4, but what's important is that it's negative. So that suggests to you that if you were to increase x from here, then x prime would decrease. So x is 0 when you're at 4. If you increase x from 4, then x must decrease. Then x prime. Okay, when x is 4, x prime is 0. Right? When x is 4, x prime is 0. And if you increase x, then x prime will decrease, which means it will become negative. It will become less than 0. And if you decrease x, then x prime will increase, which means x prime will become positive. So x would be increasing. Okay, and now we can do the same thing for the critical point 5. See what we get. Oh, we got 0. So what happens there? That 0 is coming from the fact that when you look at the plot of x prime versus x, it was like this, just barely touching 5, like that. So what's the deal with 5? What's going on? Can we know whether the arrow here is like this or like this? It actually could be either way. So just given this information, given only this information here, we cannot know which of these two behaviors is correct. If you make x be a little bit greater than 5, we cannot know if x is going to increase or decrease just knowing this. Okay, so what can we do? Well, you can pull other tricks. Just think about df dx. So, just think about f of x itself. What do you think will happen if you make x very large? I mean, you don't necessarily just have to think about values of x right here, right up against 5. You could think about values of x over here, or way, way off to the right. Way off to the right, much, much larger than 5. They should all have the same sign, right? X prime, if x prime is a little bit positive here, then it'll be also positive over here and over here and over here. And if it's a little bit negative here, then it'll also be negative here and here and here. So it's enough to think about the sign of x prime way off to the right. So now imagine plugging in a very large value of x into here. What would you get? So here you'd get a large positive number times, this would be a very negative number, times, and then this would be, well, it's squared, so it's a positive number. So large positive number times definitely a negative number times a positive number. That will be negative. So you expect this kind of behavior. And here is your phase diagram. So we have now completed this part of the homework problem. And we found the 3 equilibria. And we have also determined their stability. So you can tell that right from the phase diagram. 0 is unstable, 4 is stable, 5 is unstable. And down here, if x starts out at 2.5 at time 0, then what value will x approach in the long term? Well, 2.5 is somewhere between 0 and 4, right? So you would have x starting like here, or something like that. Then what value does it approach in the long term? Well, we know if it's here, it's going to increase. And it's going to keep increasing and increasing and increasing, and it'll approach 4. So we know it'll approach 4 in the long term. Now, you might be wondering, how do I know it'll approach 4? How do I know it won't just keep increasing past 4 and go approach 5? Or maybe increase past 4 and past 5 and approach infinity? How do we know? Well, in order to increase past 4, in order for the value of x to increase past 4, then at some time, t, it would have to equal 4, right? You can't pass over 4 without ever equaling 4. And if it equals 4, then x prime would be 0. That's what it means to say 4 is a critical point. So if it ever equaled 4, it would stop changing there, right? So if it ever hit 4, it would no longer change from there. So definitely you cannot pass across 4. Now, due to existence and uniqueness theorem that we will mention at some point later, pretty soon, maybe in the next lecture, it's actually theoretically impossible for x to hit 4 and then stop there. It just wouldn't work that way. It would just approach 4 forever, always getting closer and closer to 4. How come it couldn't approach something else forever and ever? Why couldn't it just like approach another point here that's to the right of where it started, but not equal to 4? Well, if it did, then x prime must be getting smaller and smaller and smaller as you approach this point from the left here, which means at this point you would expect x prime to be 0, considering that x prime as a function of x is this continuous function. But if x prime were 0 at this point, then it would be a critical point, so it would be one of our yellow dots here, and we got all the critical points. There's 0, 4, and 5. There are no more. So it's very important for this analysis to work, it's very important that you actually make sure you get all of the critical points, not just some of them. Okay, so if x starts at 2.5, then in the long term it must approach 4. Alright, so that's all stuff that we can say about this differential equation without solving it. We have not even solved it. So I don't want you to do this on your homework to actually solve it, but I'm just going to do it now to generate some animations to help you see kind of in a picture what's the difference between looking at a phase line versus looking at time series plots, which is what you're used to, what you've been plotting. So let me go to Mathematica. Actually, first, let me write down the differential equation again. It's x prime, so dx dt, equals x, 4 minus x, 5 minus x all squared. And this is separable. So we just have this nasty integral to do. And that will get us a solution. So let me go ahead and do that integral in Mathematica. Sorry, this is an x, just to be clear. So let me go ahead and do that in Mathematica. So I'm integrating that with respect to x, and I'll just have it do the indefinite integral. And it's a nasty integral, but I think it's doable, probably using partial fractions or something like that. And there it is. So I don't, it's not that fun to do partial fractions, right? Okay, so this is x. Now, can I actually get an explicit solution? So I know this is going to be equal to the integral over the right-hand side, which is t, and then maybe plus c. Okay, so then let me copy and paste this. Basically what I have is this equation, like this. This stuff is the left-hand side equals t plus c. And I'm just using lowercase c rather than capital because Mathematica uses capital C for something else. And I want to solve this for x to get an explicit solution. So solve that equation for x, and you can see I'm using 2 equal signs to indicate that this is an equation, not an assignment. Okay, here we go, it's thinking, and the system cannot be solved with the methods available to solve. Okay, if Mathematica can't solve it, probably I can't do it either. So maybe there's a way to solve it, but it looks, to be honest, it looks like a transcendental equation. It looks like there's just no way to get an explicit solution, x equals something. So the best we can do for this differential equation is this kind of solution here, where you have a relationship between x and t, but you don't have x equals something in terms of t. Okay, so how do I make my plots and animations? Again, this is not something you have to do. I just want to make some visualization to show you what's going on. Okay, so since the analytical approach of trying to solve up here didn't work, I decided to numerically solve using Mathematica. So there's this command that lets me get a numerical solution to the differential equation. And we will get into what that exactly means. And eventually we might have you actually make some of these yourself. But for now, you can just know that it's a way of getting an approximate solution to a differential equation, which I'm giving the differential equation here, given an initial condition. So it's not giving me a general solution. I have to give an initial condition. And then it just tries to use the information of the differential equation to step forward in small time steps and approximate what's going on. So here I've saying numerically solve this differential equation with the initial condition x of 0 equals 2.5, which is the same initial condition that that we were thinking about here with x starting at 2.5, and we said, oh, it'll go to the right and approach 4 on the phase line. So here's a plot of what happens. So this is plotting x of t against t. So this is not a phase diagram. The horizontal axis is t here, and the vertical axis is x. And you can see we start at 2.5 as requested. That's the initial condition. And then what happens in time? Well, it increases and approaches 4. You see? It's approaching 4. So it's doing exactly what was expected. What if we start out not at 2.5, but what if we start out at 4.5, between 4 and 5? Then I'd expect it to go down towards 4. So let me change the initial conditions there and rerun this. And yeah, you can see it starts out at between 4 and 5, and then it decreases, and it's asymptotically approaching 4. If I show you the plot for a longer time, it'll just look like a flat line, just decrease, and then it's really just approaching 4 forever. All right, how about if we start out x here? If x of 0 is, let's say, 7. Then it starts up a little bit off the plot up there, and it goes down towards 5. You see? What about -1? If it starts here, then I expect it to decrease forever. So put -1 here. I may be running this for too long. Hang on. All right, I'm back, and I think I have an idea of what's going on. Basically, if I run x for even a very short time, then you can see from -1 it just decreases like crazy. It decreases very quickly. So I think the numerical setup is just not handling the extremely large steps in the changes in x. Okay, anyway, that's not important. That's a numerical artifact. And what we're really seeing is, starting from x equals -1, x is going to decrease like crazy. Maybe if we start from something not so negative, like -0.01, then I can, let's plot up until 1 unit of time. That looks a little bit less insane. So basically a numerical solution is going to rely on subdividing the time axis into little intervals. And if the intervals are not small enough to handle the changes to x, then you would expect extreme amounts of numerical error, and nonsense like that can happen. Okay, anyway, let me go back to plotting from 0 to 1 here. Let me go back to the initial condition 2.5, where we can observe it sort of, let's plot from x equals 3 to x equals 5. We can observe it starting from, 2 to 5. We can observe it starting from 2.5 here and going and approaching 4. Let's go and animate that on the phase line now. Okay, so here I've adapted what I had from the previous lecture for animating things on the phase line. And you can see these, so here's the phase line. And this line segment is running from, where is it? From x equals -1 to x equals 6. So it includes the dots x equals 0, x equals 4, and x equals 5, which are these yellow dots. Those are the critical points. And I'm including as a green dot my previous numerical solution that I just showed you how I got. And you can see as I play this animation, so this green dot is starting at 2.5. If I play this animation, it moves to the right and approaches 4. And what you're seeing is in real time, where the time axis is literally time, you're seeing this behavior here.